All right. Hey, everybody. So, welcome back to another lecture. Today, we're going to move on from I think last class we did some eigen decomposition stuff. Today, we're going to move on to this topic called SVD, orthogonal basis, SVD. And the title of today's lecture is How Does Social Media Brainwash Us? Okay, so part one, we previously learned about how to project a point on multiple bases, right? So we start off, let's say you have a point here, and you're projecting it down to some vector. Right, so we learn how to perform this type of projection. That's projecting down onto 1D. Over here, if you're projecting down to multiple dimensions, so if the blue point is trying to project down to the two-dimension plane, it's going to land somewhere here, right? In order for us to do that, all we have to do is project it twice, once to this vector, second time to this vector, and sum up the result. Now, the key that you need to remember is that this type of projection only works if the basis is already orthonormal. You can't really do it otherwise. If they're not orthonormal, forget about it. So this indicates to us that finding the orthonormal basis is very, very special, right? But most bases, you can imagine, are not nicely orthonormal, right? Most bases are not orthonormal. And let's say we have a set of bases, right? Here's a set of bases. And if you may remember that when we have a set of bases, very often you end up with redundant bases, redundant bases. And when you have redundant bases, well, it means that it's not contributing, right? There's some kind of dependency here. And when you, what we want to do normally is to convert these set of bases into an orthonormal basis. After this conversion, then we work with the orthonormal basis because they span the same space anyways, right? So in the last lecture, when we start talking about eigenvalues, eigenvectors, we found out that if a matrix is symmetric, which implies that if you were to find the transpose of that matrix, right, if the matrix is symmetric, then the eigenvectors would be orthonormal. So that's a very specific condition. So if we happen to have a symmetric matrix, right, then so this matrix are the basis vectors, then we essentially can guarantee to be able to find orthonormal basis. Okay. Right? And the key takeaway is that once you go from your original basis, original, to the orthonormal basis, they span the same space. Okay, that's a key to remember. This implies that we can essentially use the eigenvectors of A. So if A happens to be symmetric, then we can simply use the eigenvectors of A as the orthonormal basis. Hmm? All right. So the first thing we want to do is that let's prove that this is actually true. That you have a set of bases. Okay. So here's V1, V2, V3. So here are the set of bases. And if you just look at it, like do a quick calculation, you could very easily test that it is not orthonormal. Right. So they're not orthogonal and they're not normalized. So it's not orthonormal. Since V is symmetric though, if we know that V is symmetric, then it implies that their eigenvectors are orthonormal. So even though the original bases are not orthonormal, notice that once we find the eigenvectors, they are orthonormal. Now, our goal is to prove that this basis and this basis span the same space. Right? That's the goal here. We want to prove that once you found the orthonormal basis, it spans the same space. And all we have to do is simply show that like each basis vector, each one of these is within the span. So if we just show that this vector is within the span, this vector is within the span, this vector. So if if a vector is within the span, it implies that the span of this vector is also within the span. So this implies that as long as each one of these is within the span of these bases, then the problem solved. It implies that they would span the same space, essentially. All right, so let's check. Well, this is the orthonormal basis. Remember, this is the orthonormal basis. And we're saying that we want to check that like each vector. So let's check the first vector. Is the first vector within the span some kind of combination of the orthonormal basis? And then you want to do that again for the second and the third vector. After after we write out this way, notice how we can pull x1, x2, x3 out, implying that we have this expression. So in order for us to find out if this vector is within the basis, all we have to do is show that we can find a point to reach the basis. Now this is easy to solve. I'm going to call this matrix U transpose x and v1, right? V1. So we're trying to essentially find the x. Okay, well, to solve this, we could just multiply the U transpose inverse on both sides. And what is interesting about that is U transpose and the inverse cancels each other out. So that's not there anymore. And another thing that's interesting is that since they are orthonormal bases, for orthonormal basis, its transpose is equal to the inverse. So this inverse can be just converted to a transpose. The transpose cancels out. This tells you that the solution is as simple as the vector times the basis. And that's it. So this is much easier than Gaussian elimination. Previously, you had to learn Gaussian elimination in order to solve the x1, x2, x3. But over here, you don't need it anymore because the bases are orthonormal. It allows you to essentially perform just instead of inverse, we use the transpose instead. All right. So what I just told you is, okay, we can find out if v1 is within the span by solving for x, right? So once we solve for x, this is the result, we can plug x back in. We plug x back into this relationship. We solve for x and we plug it back in. So if x is equal to u v1, so let's plug u v1 here. And therefore, over here, it gives us u transpose u times v1. So if we verify that this statement is true, then it means that v1 indeed is spanned by u. Okay. Now we have three bases, so we just have to do this 3 times. Okay. What I mean by that is, remember we had v1, v2, v3, right? So we can stack them together. So if we take v1 times this, remember this is that equation we just solved. This is the test we run. If we run this test and the left side is equal to the right side, it means that it's within the span. So now if we just do this 3 times, once, twice, 3 times for each vector, the result should be equal to v1, v2, v3. And we can further simplify this. U transpose U can be pulled out. So I pull U transpose U. And then V1, V2, V3 end up becoming a stack together as a matrix is equal to V1, V2, V3. So this right here gives us the final relationship. It's saying that if this statement is true, so you have basis vectors V, and you want to know if they're spanned by the orthonormal basis eigenvectors. So if you run this test, you multiply it, and if it is equal to V, then the problem is solved. And yes, this will verify that they are equal, and it verifies that orthonormal basis spans all the bases. All right. That was a lot to take in. So I think it's better to pause here so that you have a second to think it through. Let's give it a try. This is the orthonormal basis, and these are the basis vectors. And you want to show that these basis vectors are within the span of the orthonormal basis. Okay, so pause the video, go back and look if you don't remember, and basically just check if first the eigenvectors are orthonormal. Right? You can use NumPy for this, by the way. And then once you check that, you want to check if the eigenvectors spans the same space as the original basis. So these are the eigenvectors. Do they span the same space as the original? Okay. Here's the solution. You can pause and study it. All right. Now, hopefully you understood that. What what if we have non-square matrix? That's the next topic. Well, for symmetric matrix, we learn how to find the orthonormal basis, right? So in the special case where our matrix is symmetric, then we know that we can get orthonormal basis. However, in life, we rarely get perfectly symmetric matrices. So this is when SVD, or singular value decomposition, was developed. You no longer need symmetric matrices to find have these kind of relationship. So to perform SVD, or single value decomposition, let's assume that our matrix is stacked this way. So notice this is not symmetric, right? It's not square. You cannot run the transpose, and it's the same. So and each row is a single basis. So you have three bases. So what we do is all we have to do is SVD is really simple. We just take, if you know eigen decomposition, if we take the matrix and multiply by itself transpose. So you can multiply B by itself B transpose, or you can do B transpose. You notice how you can do either way. If you do it this way, notice you get a symmetric matrix 2 by 2. If you do it this way, notice you get a symmetric matrix 3 by 3. So you can always convert any matrix to a symmetric matrix by multiplying by itself. Now, if we find the eigenvectors of this matrix, it's going to be length 2, right? Therefore, this length 2. This implies that these are the eigenvectors of the rows. Remember, this is the row space. But if you multiply the other way, now the eigenvectors are 3. So this would be as if you treat these as the vectors. So now the eigenvectors are 3-dimension. So you can get the eigenvectors if you treat the matrix as either row space or column space. Either way, you can get both of them. So SVD essentially allows us to find the orthonormal basis even without the symmetric matrix. So we don't need to know the symmetric matrices. SVD just says do this initial conversion and then you will be able to find it. Now, because you do B times B transpose, you need to take the square root of the eigenvalues because you multiply twice, right? So you have to take the square root. And what we do is we calculate the eigenvalues and we take the square root. And this is called a singular value from singular value decomposition. From the singular value decomposition. And the eigenvectors we get are no longer called eigenvectors. They're called singular vectors. So if you have a symmetric matrix, then you can easily solve for eigenvalues, eigenvectors. But when you don't have symmetric matrix, then you have to convert it into a symmetric matrix, and then you will get singular value and singular vectors. And the intuition for singular vector is very similar to the eigenvector. All right. So that's the point. Okay. So let's just try it. There are a lot of concepts right now you need to understand. And the only way you will know it is just try it. So let's say we have this matrix B. So given this B, let's do this by hand. Let's say that your some or singular vector consists of the row space. Okay, so these are your basis vectors. So what would be the singular vector if you treat it that way? And the second question is, if you treat it this way, how would you solve it? Now, once you find your singular vectors, you can give this a try. You will see that your singular vector spans the same space as the original basis vector. Okay. All right. So here's the solution for part 1, solution for part 2, solution for part 3. Okay. All right. Give this a try. Give this a try. This hopefully will be helpful. Okay, next we can move on. The influence of social media on our opinions. So in the previous lecture, we learned about symmetric matrices, right? Here's a symmetric matrix, and with a symmetric matrix, we can decompose them into three matrices, right? And the three matrices then reconstruct the matrix A. Well, with singular value decomposition, we have a very, very similar idea. So this is if the matrix is symmetric. But if the matrix is not symmetric, we will essentially have this relationship instead. Okay. Now V right here is the eigenvectors of the column space. And U here is the eigenvectors of the row space. Okay? So the way it works is we would have column space, let's say it's V1, V2, V3. And then row space would be U1 transpose U2 transpose U3 transpose. And sigma here is the singular values. So it would be square root 2.5. Right. So okay. So this is the continuation of the practice question we just did. So basically, when you solve for it, you end up solving for column space eigenvector, and then a row space, and then the singular values. Well, it turns out that if you simply multiply them together, it reconstructs the matrix, original matrix, just like the symmetric case, right? So this is the case when it's not symmetric. This is the case when you have a nice symmetric matrix. Okay? So therefore, if we use SVD, singular value decomposition, it is a more accurate model than if we just assume people are symmetric. All right. So now we have enough background to model social media. Let's say that we model the way you think about a specific topic with some basis vectors, right? So this is how you think about a particular topic. In today's example, let's say we talk about beauty. Like, what is it? The way you think and your opinion about beauty is, let's say, is aligned based on these two factors, and together your opinion, the way you think, is modeled by this matrix B. Okay. Well, every time we're exposed to a certain content, we're going to call that content A. It's equivalent to your matrix interacting with the content. Right? So you start with some initial point and you interact with the content, and your opinion change a little bit. Right? So the way it works is like you at any given point, if you interact with the content, it changes your opinion. So you can imagine if you multiply once, then you got B1. And then if you have B0, you interact with the content multiple times. 1, 2, 3, 4, 5. So this would be 5, right? As you continuously get exposed to the similar message, your opinion will keep changing, right? So we put the lower index here to represent like how many exposures you've had. So the way it works is that the content is trying to convince you some kind of message. And the eigenvector of this content is the essence of the content. It's essentially what the message is trying to convince you of. What happens is, as you get more and more exposed to this content, your opinion becomes more and more aligned to the eigenvector of the message. So we can see the impact of being repeatedly exposed to false reality. So I ran like a simulation. So let's say we talk about beauty, right? So let's say that we have two lines. So let's say over here is reality, over here is reality, and then you have a zone of just like delusion. So this is delusion, the black part. And this right here is a vector pointing living in the space of delusion. So if you start at some point where it's relatively true, right? This is reality. You start at that point. However, if you get exposed to the message again, 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 the way you think actually becomes aligned to the dominant eigenvector of the message. So it's constant. You're essentially changing your opinion, right? You can kind of see it this way. So it doesn't matter. So the first vector was 0, 1, right? So 0, 1, and 1, 1. So notice how this vector is 0, 1, and this vector is 1, 1. So those are the two vectors representing your opinion about beauty. And if you simply multiply the vector by A over and over and over again with multiple exposure, eventually this vector is going to convert into this, and this vector here is going to convert into here. Both of which basically tells you that you end up believing the message essentially, and it changes your perspective. So over here, right over here, here's a perfect example of an ad. What we like when we see ads like this, it essentially give us a sense of multiple messages. Of course, one of the message is that Professor Wu is awesome. However, there's another message which we are exposed to all the time. And that other message is that being flawlessly beautiful is quite common. If we see a lot of pictures with a lot of beautiful people, our perception gets biased little by little into the region of delusion, right? A region of like that's just delusion is the best word. And then your opinion about what is beautiful and stuff end up being like changed. So the repeated exposure, this repeated exposure, like essentially, is essentially how we can change a person's opinion. Right? So, so what I said here is, let's say you have two exposures, right? So it's essentially you start with opinion 0 times 0, and then you got exposed twice, boom, boom, and then you got 2. Well, another way to write this is instead of write a twice, it's a squared. So this multiplied by a squared gives you b2. And then if you get exposed more times, then it's 3 times. 1, 2, 3. So you got exposed 3 times, it's a3. So if you instead, I mean, we could just take our initial matrix and multiply by a again and then again and then again. However, it actually makes more sense if we simply know how to calculate a to the third. Okay, so here's a natural question. How do you calculate a to the third power? a matrix to the power. This is something we haven't done in the past. Right? And by knowing what x to the third is, it essentially allows us to figure out that after n number of exposures, where would you be? Okay. So therefore, the mathematics of brainwashing is essentially the understanding of matrix power, a to some kind of power. Right? So let's say we have a to the fifth power. So like I told you, you could just multiply b by a 5 times. 1, 2, 3, 4, 5, right? But you don't want to do that. What if you have a to the 1 million? Then then it gets very, very complicated. You could take you a long time. Instead, can we just know what this is? Okay. Well, instead of doing it this way, let's keep our model simple. And let's go back. Instead of talking about like non-symmetric matrix, let's start off with assume again that we are dealing with symmetric matrix and square, symmetric and square matrix. And therefore it implies that we could break the matrix down into this relationship. Right? So this was the relationship we learned previously. We could break a matrix down into its various components. So this component is the eigenvector, this component are the eigenvalues. So the question now is then, can we use this knowledge to apply and learn what a to some kind of power is? And it turns out, yes. The answer is, if you want to find a to the power of n, it is simply a to the power n. You take the power of the eigenvalues. Okay? That's it. That's it. And of course, you're thinking, okay, you take the power here instead. But is this actually easier? And it turns out, yes. This drastically simplifies how to find the power. Okay, so let's see why it's easy, right? As long as we know how to find the eigenvalue. So let's say we have this matrix A, and after we perform decomposition, we have A, and then it becomes V, some kind of matrix eigenvalue. Well, it could be lambda or sigma. Let's use sigma here. V transpose. Is that right? Okay. So the three vectors, okay, let me write this again. A is equal to V sigma V transpose. So let's copy V here. V, this one is sigma. Well, I call it lambda. So lambda, and then V inverse. So what I'm telling you right now is that notice we have this matrix A, and I'm taking the power to the n, to the power n, right? And instead of trying to calculate this multiplied by itself n times, we just need to realize it's equal to this to the power of n. Now, why is this easier? Well, take a look. If we try to do power of 2, notice how when you actually multiply them together, it's simply 4 square, 2 square. So power of 2 is just the numbers square. What about power of 3? Well, it turns out to be 4 cube, 2 cube. So calculating this is really easy. And then if we know the eigenvectors, we can calculate the power this way. Yeah. So this means that calculating any power, all we have to do is perform the diagonalization, eigendecomposition, and then take the power to the eigenvalues. And this right here will essentially allow you to calculate a to the whatever number you want to the bn. Now, why does this work? Well, let's take a look. So if a can be decomposed into into this relationship. Therefore, a squared is simply a times a, right? So let's copy a down twice. But notice this is the inverse of this. That means matrix times its inverse is cancels each other out, right? Cancels each other out. Therefore, notice how we end up having lambda multiply with each other square. And the idea continues, right? If you have square and you multiply by yet another matrix A, notice how V inverse cancel each other out again, becomes lambda to the cube. And this is why this relationship works, why you can take power through only using the power of the eigenvalues. Now, the same idea extends when A is not square, right? If it's not square, now remember you need to multiply A by A transpose. And then if you want to increase the power again, you're going to multiply by A again, A transpose. So by rotating this, you can essentially constantly multiply by the same power. So let's say if we have singular value decomposition, remember A is equal to V sigma U transpose. Therefore, A times A times A is equal to this. And remember, if you have U times U, that cancels each other out because U transpose is equal to U inverse, right? Because U is symmetric, is orthonormal. Therefore, sigma times sigma becomes sigma square. So you can see that you can have many powers as well, even when the matrix is not symmetric. Okay. All right, let's do simulating matrix power with eigenvalues. Let's say we have some add, and this is the add, and then you want to write a Python program and perform eigen decomposition or diagonalization. And then what I want you to do is to compute a cube different ways. First way, just multiply a 3 times. And the second way is to perform the eigenvalue decomposition and then take the power to the third, like such, right? So do it both ways to convince yourself that they result in the same thing. Right? So this is your next exercise. And for our final exercise of the day, you'll go, this is the final, right? Yeah, this is the final. Your goal for putting every comment, yeah, your goal is that here's a message, and this is you, right? This is you. And you are being exposed and bombarded by this message over and over and over again. What I want you to do is, by hand, calculate the eigenvalues and eigenvectors of the message. And then I want you to confirm that A is indeed equal to V, equals to this decomposition. And then once you identify the dominant eigenvectors of A, right? Once you identify the eigenvector with the largest eigenvalue, then you can use Python. With Python, I want you to confirm that A to the 100 is equal to this. And then this essentially simulates what happens if you get exposed to the same message like 100 times. Once you simulate this, you can essentially figure out the you can normalize each column. So what I mean is, as you get exposed to this, your vectors are going to change over and over and over again every single time you get exposed to this. So after 100 times, you want to basically figure out the unit vector for each and every one of them. the unit vector should point in the same direction as the dominant messaging of A. Okay, so that's it. Pause the video and do this. Here's the solution for the first part. This is the dominant eigenvector. There's also the code solution here. So I think that is it for today. I will see you in the next lecture.